Kia ora class, today we're doing the Level 3 Organic NCEA paper from 2019. So our first question is naming and drawing. Someone's already had a crack at this paper and they've made a mistake, so it wasn't me this time. So let's count these carbons, 1, 2, 3, 4. Alright, so we've got a 5, so we've got a pent. This part here tells us it's an aldehyde, and then we've got a chloro here. We're going to number this 1, 2, 3, 4. That's a mistake that this person's made, so it's actually a 4 chloro pent anal. 4 chloro pentanal. Don't need to name the anal because it's on the end. Okay. Ethyl hexanoate. So this is an ester. The hexanoate group is going to be the COOH that provided the double bond O, and the ethyl group is going to be what was an alcohol. So we can draw that out. It's going to be CH3 single bond CH2. And then a single bond to the oxygen. So that was my ethyl group with my 2 carbons. On the other side, I've got a carbon double bonded to an oxygen, and this is a hexanoate, so I need 6 carbons. So we'll put a hydrogen, no, not going to have that one there. We're going to put a CH2, 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 1, 2, 3, 4, CH2, CH3. Right, so we've got our 6 carbon carboxylic acid, which was the hexanoate, and we've got our 2 carbon alcohol, which was the ethyl. Okay, down here, what have we got? We've got a methyl side group, and we also have an amide group. So this is going to be 1, 2, 3, 4. So that is butanamide. And then name the side chain. This is 2-methyl. Alright. Propanol can be formed from the oxidation of a primary alcohol. Draw the structural formula of the primary alcohol and explain why distillation is required to obtain the aldehyde product during the oxidation process. Okay, so prop means it's got 3 carbons in it. So what is the structural formula of a primary alcohol with 3 carbons? That's pretty easy. Okay, so there's our propanol. Why distillation is required to obtain the aldehyde product during the oxidation process. Okay, so during this process we are going to be using heat to convert the alcohol to the aldehyde. However, this can be further oxidized to carboxylic acid. Okay, so the fact that it can be further oxidized means that we need to remove the aldehyde as soon as it's formed. So we can remove it based on its boiling point. Alright, so that is why we can use distillation to get rid of the aldehyde before it's further oxidized to the carboxylic acid. Alright, next question. Chemical test to determine or distinguish between different types of molecules. We need to include reagents that we use and conditions. So conditions, we're thinking, is it acidified? Do we need to heat it, etc. Observations, we're looking for color changes or bubbles or something like that. Reaction type, okay, and also structural formula. So the first one, we've got an alcohol, and we've got a double bond. So let's just use a simple one. There's a few things we could do here. Real simple one is Br2AQ, aqueous bromine water. The orange solution will be rapidly decolorized. Okay, so it goes clear. Orange solution is rapidly decolorized. That indicates the presence of a double bond. Okay, this is an addition reaction. Really easy reaction. You're breaking the double bond, adding 2 bromines in, and the molecule that it forms will be 1,2-dibromoethane. And of course, nothing will happen with the alcohol. Alright, so now we've got an aldehyde and an alcohol. Okay, so both of these things can undergo oxidation reactions. The alcohol can be oxidized to an aldehyde, and the aldehyde can be further oxidized to a carboxylic acid. So if we're using dichromate or permanganate, they would both be oxidized and we'd see the same thing. But there's 3 things we could use here. We could use Tollens reagent, or we could use Benedict's or Felling's solution. Okay, now these will oxidize the aldehyde to carboxylic acid, so will that. And the observation with Tollens reagent will get a silver mirror, and with Benedict's and Felling's we get sort of a brick red precipitate. Okay, and again it's going to form COOH. Okay, so carboxylic acid from the aldehyde, the alcohol cannot be oxidized with just Tollens, Benedict's or Felling's. It needs dichromate or permanganate acidified. Alright, so ethanol chloride, so this is a OCl, this is a acyl chloride, and ethyl pentanoate, this is an ester. So what could we use here? Well, we could just add water. Okay, and the ethanol chloride, the acyl chloride, will vigorously react. Okay, it's a really vigorous reaction because it forms COOH and HCl gas or fumes. Okay, and that's why you get those white fumes. So nothing will happen with the ester again. Okay, this is a question that requires a little bit of critical thinking here. So let's just try and break this down. We've got 3 unknown organic molecules that we've got to come up with one leading on from the other. So start off, W is a straight chain organic molecule with the molecular formula C4H6OCl2. Okay, straight chain, so it's the 4 carbons just in a straight line. It's got the following properties. Does not exist as enantiomers, optical isomers. Okay, so that means that every carbon must have 2 ligands the same, at least. Produces steamy fumes with water. Okay, fumes with water, this is kind of like this previous question here. We're thinking acyl chlorides now. Okay, so that's a clue for us. This is an acyl OCl, an acyl chloride. Okay, it reacts with excess ammonia to form product X. Product X turns damp litmus blue. What turns damp litmus blue? Bases. What's the only base in organic chemistry? Amines. Okay, so X must have an amine part to it, and we can also react W to form X. Product X undergoes acidic hydrolysis to produce product Y. Bubbles are released when product Y reacts with sodium carbonate. Okay, so bubbles are released when product Y reacts with sodium carbonate. Sodium carbonate is a base. that means that Y must be an acid. Okay, it's doing an acid-base reaction releasing carbon dioxide gas. Alright, let's start with W. Straight chain. So let's go 1, 2, 3, 4 carbons. Alright, we know that it is an acyl chloride because it fumes with water. So we'll put the double bond O bond Cl in. So we've got the acyl chloride part to it. It's a straight chain. What else have we got to use here? We've got this extra chlorine, so it's 2 Cls. So where could we put that? Well, if we put it anywhere other than on the end, there will be a carbon that has 4 different ligands to it. Therefore, it would create optical isomers. So we have to put the chlorine on the end, fill it in with hydrogens, and that's our molecule for W. X, product reacts with excess ammonia. So when we add NH3, excess, we get this thing. Okay, so NH3 is going to react with a couple of things here. One, it's going to react with this chlorine, and 2, it's going to react with this chlorine. So a couple of substitution reactions here. So let's draw that out. So at this end we get an amide, CH2, CH2. Those just stay the same in the middle. On this end we get an amine. So now we have an amine and an amide, and that works for this because we know that it's going to turn as blue. This is going to be the amine end, not the amide. Amides aren't basic, but amines are. Okay, and now this can undergo acidic hydrolysis to produce an acid. So what we're looking for here is how can we turn this into a carboxylic acid by adding acidic water. And so this part here of the molecule is going to form a carboxylic acid. Okay, CH2, CH2. Now remember, when we talk about hydrolysis, that means using water to break up a molecule. And so we've taken off the NH2, we've added an OH, so we need to add another H as well. So we'll add our NH3 in there and make this whole molecule, charged. Okay, so that is our carboxylic acid with this extra NH3 group. Two chlorobutane can exist as enantiomers, optical isomers. Draw the enantiomers in the box below. Alright, so I'm going to put my center line in here. This is like my mirror line, and obviously this is my chiral carbon here. This carbon has 4 different groups attached to it, so I'm going to just put my carbons in the middle. I'm going to go straight up with my chlorine, that's an L, and then I'm going to go into the middle with my CH3, Doesn't matter how this was written, CH3 or H3C, it's fine either way, just as long as you've got the CH3 coming towards the middle. Okay, so these are my first 2 straight lines. Now I'm going to start doing my solid triangle. This indicates that it's going into the page, and I'm going to put, I've done the CH3, I've done the Cl, I'm going to put the H at the bottom for both of them. Okay, and then going out of the page, I'm going to put the rest of this molecule here, the CH2, CH3, so CH2, CH3, CH2, CH3, and those are now mirror images of each other, kind of like your hands, right? You've got the CH3s in the middle, you've got the Cls up top, you've got the hydrogens down the bottom, and then the CH3s on the outside. Okay, how can we distinguish between these? We can shine plain polarized light will rotate in opposite directions. So one of them will rotate at 90 degrees left, and one will rotate 90 degrees right. Okay, flowchart time. So we have a reaction scheme here, and we are starting with a chloroalkane. So we've got a chlorine group here, so that's what I'm immediately looking at, and reacting with KOH alcoholic. This is telling me this is going to be an elimination reaction, and we're looking for the minor product. Okay, so in this case, removing the chlorine and removing one of these hydrogens. Most of the time this hydrogen is going to get removed because there's the least number of hydrogens on that carbon. Some of the time, less of the time, this hydrogen is going to get removed, and so my minor product is going to be where this one loses the hydrogen. Okay, so that is my minor product. Now, HCl, we've got a double bond here, so there's going to be an additional reaction. HCl being added across the double bond, again, they want the minor product. Okay, so if I add a hydrogen, most of the time it's going to go to the carbon with the most hydrogens, and less of the time it's going to go to the carbon with the least. So this is CH3, CH2, single bond carbon, and this time with the minor product this carbon gets the extra hydrogen. Okay, I'm doing these lines just to help show it really clearly so I don't forget any bonds. Cl, H, H, whereas this is really easy to just write CH3, CH2 because it's not changing. Okay, how can I get from there to there? We've done this reaction before. This is NH3 alcoholic or concentrated, so there's a substitution reaction which we did on the previous page or the page before. Okay, and then KOH aqueous, this is going to be a substitution reaction instead of the elimination reaction we get up here with alcoholic. With aqueous it's a substitution reaction, so we're going to substitute that Cl, so two substitution reactions here. CH3, CH2, that's going to be the same, CH2, CH, H, and then the chlorine there becomes an OH. Okay, so we're making an alcohol here. Alcohol to carboxylic acid, how do we do that? That's classic oxidation reaction. Acidified dichromate, you could have also used acidified permanganate if you prefer. Okay, what are we doing here? Okay, this functional group here, this is an amide linkage. So how do we get from an amine to an amide? Well, considering that that's a carboxylic acid, and we've got another step before we get to this, this is going to be an acyl chloride. Okay, so CH3, CH2, CH2, single bond C, double bond O, and then the OH has become a Cl. So how did we get from there to there? Yes, it was Cl2. Right. C5H10O can exist as a number of different constitutional structural isomers. Okay, so we're using these atoms, arranging them in a different way. Straight chain molecule that forms a silver mirror when heated with Tollens reagent. Okay, so this is going to be an aldehyde. Alright, so we'll draw the aldehyde functional group in first. Put a carbon, put a double bond O, put a single bond H. That's our aldehyde functional group. And it needs to be a straight chain molecule. So CH2, 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 1, 2, 3, 4, and one more CH3. So count the hydrogens, 1, 2 is 3, 2 is 5, 2 is 7, and 3 is 10. C5H10O, straight chain, aldehyde forms a silver mirror. Branch chain that does not form a silver mirror. Okay, not forming a silver mirror. What cannot be oxidized but contains an oxygen? I'm thinking this is going to be a ketone. Okay, so we'll put a carbon in the middle, double bond O, and we're going to have to do carbons off each side because this can't be oxidized any further, whereas the double bond oxygen on the end can. Okay, but we need a branch chain as well, so let's say that one branch is there. Put a hydrogen on there to finish it off because it's the end of the molecule, and this is an H3 as well. You just count those hydrogens, 3, 3, 3, and 9 is 10, and there's the branch there, and it's a ketone so it can't be oxidized. Cool. 5-ring cyclic molecule that forms steamy fumes when reacted with thionyl chloride. Okay, so this is going to be an alcohol because alcohols will form HCl and SO2 when they react with thionyl chloride, so we need to do an alcohol, and it's a ring. So easy, we just start with a ring of carbons. That's a C. Alright, has to be an alcohol to form these steamy fumes with SOCl2. So we'll chuck an OH on there, and that becomes CH2, 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 CH2. Just one more hydrogen coming on there. 1, 2, 3, 4, 5. Lots of hydrogen. That works. Okay, straight chain secondary alcohol. Okay, so the OH group attached to a carbon that's got 2 other carbons that decolorizes bromine water. That means it's an ene, it's got a double bond, and can exist as both cis and trans geometrical isomers and optical isomers. Wow, a lot going on here. This means we've got a chiral carbon. This means it's got a double bond, and each carbon has got different things attached to it. AB, CD, or AB. Okay. Secondary alcohol. So let's just start with what a secondary alcohol would have to look like. Carbon with an OH group on it. Going to have to be attached to 2 other carbons because that's what makes it a secondary alcohol. Now I need to get a double bond in somewhere. If I throw it in here, I don't think we can get cis and trans. So if I throw a double bond in here now, because if I throw a double bond in there, it's going to have to be a branch chain, and then the double bond in there, CH3. Of course, that one there. So 4 hydrogens, 5, 6. Oh, need another one there. Straight chain, yes. Secondary alcohol, yes. Decolorizes bromine water, double bond, yes. Cis and trans, that carbon has got a hydrogen and a CH3 on it. That carbon has a hydrogen and then that thing on it. And you could flip those hydrogens around. So yes, cis and trans. And optical isomers. Do we have a chiral carbon? Where's the carbon that's got 4 different things attached to it? That one. It's got a CH3, an OH, an H, and then all that thing. So that works. Ticks all our boxes. Okay, question 3. Looks like we're on to questions on polymers and triglycerides here. So we're thinking about monomers and polymers and what sort of condensation polymerization versus addition polymerization here. Nylon is used to make airbags. The monomers used to make nylon 6,6 as shown below. Okay, so look at this. We've got a acid group, and we've got an amine group. So it's going to be an acid-base reaction, isn't it? In the box below, draw a section of nylon 6 into 2 repeating units. Alright, so just going to start with this molecule out here. It's going to take up quite a bit of space, I'm guessing, so I'm going to start over here. H2N single bond brackets CH2 brackets 6. Now here, when this molecule reacts with this molecule, the OH comes off there, and a single H comes off there. So the N single bond H single bond carbon double bond O. So that carbon that had the double bond O single bond OH, it lost this. It joined up to the nitrogen, which lost a hydrogen, and so then we just continue on that molecule there. CH2 brackets 4 single bond CO. Okay, and now, that's my mistake, it's going to start repeating back again here. So we need to lose that OH from that molecule there, so scribble that out. Straight line, carbon, double bond O, joining onto this side of this molecule, single bond N, up to the H. See how we're just flipping this one around, kind of, joining, same join but the other way. And now we just finish off this molecule. CH2, 6 of them, single bond N, so that's 1, 2, that one's there, that molecule is there, this molecule is in up H, this is going to get big, C double bond O, CH2 brackets 4 single bond COOH. Wow. Alright. That first part is there. That part is there. That part is that. And that part is that. So 2 repeating units of these monomers. Explain why this is referred to as condensation polymerization. Okay, well we talked about that before. We're removing H2O and joining together 2 molecules to make a larger molecule. So you're removing a small molecule when you're joining two molecules together. Okay, triglycerides are found in fats and oils. Below is an example of a triglyceride circle and ester group. Okay, so that is an ester group. That is the other ester group, and that is another ester group. So I'd say circle 1. I circled 3. Maybe lose a mark there. Compare and contrast the acidic and basic hydrolysis of the triglyceride molecule on the previous page. Okay. Hydrolysis of an ester is, the rule is break where you make. So kind of like up here, we're going to break them right in the middle of that ester linkage. Okay, so that's where they would break. This is going to go back to being the acid. Okay, and this half is going to go back to being the alcohol. In a acidic hydrolysis, but then we'll look at the basic one in a second. So explanation of the hydrolysis reaction is using H2O to break a molecule. That's the basics of hydrolysis. Okay, structural formula of the products used, reagents and conditions required. Okay, So let's just draw this out. In both cases, acidic and basic hydrolysis, we're going to get the same alcohol, right? Glycerol. So we'll draw that out. It's going to be carbon, hydrogen, hydrogen, OH, carbon, hydrogen, OH, carbon, hydrogen, hydrogen, OH. Okay, so that is this molecule here when you hydrolyze it and break the ester bond. Okay, and you get a triol, and this one's called glycerol. In acidic solution, now we're looking at what happens on this half of the molecule. We're going to get carboxylic acid. We're going to get 3 different carboxylic acids. So it's going to be carbon, double bond, O bond, OH, single bond, CH2, 14 of those, and then a CH3, times 3. Because you see, these molecules aren't joined together, whereas that glycerol molecule is. In basic conditions, well, pretty much the same thing, except when this is in a basic solution, it's going to act as an acid and donate that proton, isn't it? So in a basic solution, we will get the conjugate, sorry, that's a mistake. We will get the conjugate base of this acid. Times 3. 1, 2, 3. Reagents and conditions required. So reagents, either dilute acid, could be HCl or something like that, or dilute base for either of them. Let's say it could be NaOH, and also we're going to need heat and reflux. Okay, we need heat and reflux just so that those products that we're producing are staying in the solution and reacting further. Final question. Devise a reaction scheme to convert butanone to butane 2,3-dione. Okay. Might be easier to attack this one from a reverse. So, how can we get to a dione? Well, if I have a double bond in here, I reckon I can do oxidation to get to a dione. So I'm going to go, if we had an ene, we could get to a dione. What could we do to get to from this to an ene? Well, how about alcohol to an ene is going to be an elimination reaction, and butanone to an alcohol is going to be reduction. Alright, so butanone plus our only reductant, NaBH4, will go to butanone plus NaBH4 will go to an alcohol. It's going to put a hydrogen on there, form a single bond there, and put a hydrogen on there, and we'll call that 1, 2, 3, 4. So that is butan 2-ol. Okay, that's oxidation. Butan 2-ol. What are we going to react to get that to go to a double bond? It's going to be an elimination reaction. What can we do elimination with? Concentrated H2SO4. Okay, it's going to rip water away, isn't it? So that is elimination, and that will form a double bond here, and we'll call that but2-ene. Probably want to draw this out in a bit more detail than I'm doing it here. And then but2 How are we going to get that to this dione? Well, the double bond's reactive. We need to oxidize it. We're going to use MnO4 aqueous. Okay, we don't need acid for this one. Otherwise, we'll probably get a diol with alcohols on it. So we just want to get rid of the acid. We don't want the acid involved. So we just want oxidation here. So this is going to be an oxidation reaction, and it's going to get us to BU2,3 dione. Done.